Hello friends, welcome back. Session 6 is going to be about linear regression. Okay, we have studied classification so far, and we said that classification was a significant category of AI problems. Similarly, regression is also an important category of problems in AI, and therefore we are going to be looking at regression. And in particular, we will begin with a special type of regression problems called linear regression problems. Okay, so this lecture and the next, we are going to be focused on looking at the linear regression problem. So let's see what linear regression is. Okay, in general, regression involves creating a model based on training data, of course, to estimate the value of a dependent variable, okay, or also called the output, given the values of independent variables, also known as inputs. So I'll repeat this once again. Regression involves creating a model, as always, creating a model based on training data. Clearly, we need training data. And we are going to create this model to estimate the value of the output given the values of the input variables. Okay, so let's see what this is with a small example. Let us say you had three different variables: years of experience, percentage of marks during graduation, and the distance that the individual lives from the workplace. Okay, so I have created a small table here of people. So this is person 1, person 2, person 3, person 4, and so on. And for each of these persons, we have tabulated their years of experience, the percentage that they received in their BCom or BS or BTech or whatever, and how far they live in kilometers from their workplace. And based on these three variables, based on these three factors, we are interested in predicting the salary of that individual. Okay, so salary of that individual. So the training data has these input variables, also called independent variables. So here the independent variables are years of experience, percentage, and distance from workplace, and the dependent variable or the output is the salary of the individual. And this is what the training data is going to look like for this particular example. Okay, so this is a small chunk of the training data, where for each member of the training data we have tabulated the values of the independent variables and the corresponding value of the observed or the dependent variable or the output, as we called it. Now in the regression problem, what we need to do is, if you are given the years of experience, let us say 7, let's say you are given the percentage in graduation for this guy, let's say 55, and you are told that he lives at a distance of 3 kilometers from the workplace, you want to estimate the value of his salary. Okay, you want to estimate the value of the salary given the values of the independent variables. So regression is about estimating the value. Okay, classification was about estimating the category. Regression is about estimating the numerical value. Okay, that's the difference. Let's look at this difference in slightly more detail. Okay, so this is what we were doing in our classification case, right? I mean, we had training data, let's say, and the input variables were age and income over here, and we wanted to predict the attire or what these men would be wearing based on their age and income. And we had sort of defined three categories. We had defined three classes, three categories, three classes, three buckets of the output. So group A, or the category 1, was the category of people who wore a pajama or a dhoti. Group B was people who wore shorts. Group C was people who wore trousers or full pants. Okay, and your training data, of course, looked like this. You basically polled a number of people you asked them their age, you asked them their income, and you saw what they were wearing, and you sort of put the category over here under attire, right? So we saw this example in the past. And then given a test input, so if you were told that there is a guy whose age is 27 years and whose income is, let's say, 50,000 rupees, you wanted to predict what he would be wearing. In other words, you wanted to predict in which category or which class that test input would fall. So this was classification problem. Classification problem dealt with classifying an input into one of several distinct buckets or categories, okay, and you trained your model based on similar training data. Okay, the training data tabulated the values of the input parameters or the independent variables, and it had a column for the output class or category. So you trained based on this, and your AI model learned, and then when you were given an age and income, you predicted the category or class of that test input. So this is what classification was about. Okay. What is regression? In regression, the data deals with actual values, not categories. Okay. So there are no categories. Okay. There are no categories. We are going to be dealing with numerical values. So for example, if you wanted to sort of predict the cholesterol levels of people based on their age and income, this value would be a numerical value. What you would do is your training data would comprise the independent variables age and income, and it would also comprise the dependent variable, which is the triglycerides or cholesterol that you wanted to predict. And you had a tabulation of this sort of training data. Note that the training data did not have categories, it had actual numerical values. Okay, so this was all about predicting numerical values. The AI model in this case, the AI model in the case of regression, is going to learn based on training data, and then when you give a specific test inputs, let's say 27 years old, 50,000 rupees salary, it's going to predict a numerical value for the cholesterol level of that person. Okay, so that's the difference. That's the difference between classification and regression. In classification, you are dealing with categories, a finite number, a fixed number of distinct categories. You are categorizing. In regression, you are predicting a numerical value. Okay, so to give you more examples, let us say whether you want to invest or not invest in a company would be a classification problem, in particular a binary classification problem, whereas predicting the value of the stock tomorrow would be a regression problem. Okay, so I think this is pretty clear, the difference between categorization, classification and regression. Okay, now when I was sort of studying classification and regression, the one question that came to my mind I want to share with you. Okay, I was sort of wondering, can regression problems be formulated as classification problems, and vice versa? Can classification problems be formulated as regression problems? Okay, so are these really two distinct categories of problems that require two different techniques, or is one of these cases simply a special case of the other? So let me tell you why I had this question in my mind when I looked at these things for the first time in my life. Okay, so remember in classification we had categories, right? Whereas in regression we have numerical values. What if we defined, a very large number of categories? Okay, a very large number of categories. So for example, if the value of cholesterol, let's say, goes from 100 to 400, or let's say 450, whatever, 500, why couldn't you define 350 categories over here? So let's say 100 to 101, 101 to 102, 102, sorry, 102 to 103, These are all categories, right? These are all categories. And then you could sort of, instead of putting the numerical value over here, you could put the class and sort of make this into a classification problem. So if you were looking, if you did not want greater than, let's say, integer accuracy, could you essentially create small buckets, tiny buckets, lots and lots of them, so as to cover the entire dynamic range of your output variable, and then convert the regression problem into a classification problem? So in other words, you would predict a class. You would say that the class or category of cholesterol for a particular person was this if his level was between 102 and 103, right? So is that possible? Can a regression problem always be configured as a classification problem? And if it can be, why do we study regression problems as a separate category of problems, right? Conversely, is it possible to configure every classification problem as a regression problem? For example, I told you about the problem of predicting, the classification problem of having two classes, invest or not invest. Now you could argue that if you defined a continuous variable, for example, the stock price 1 month from today, that would be a continuous variable, and depending upon whether the value was higher than today's value or lower than today's value, you could decide whether the output needs to be in bucket 1 invest or bucket 2 don't invest, right? So can you configure every classification problem as a regression problem? So I mean, are these two categories of problems really distinct, or are they sort of not all that distinct? So this was a question that I had in my mind, and when I sort of thought about it, I think the answer sort of made itself clear. But if you like, you can stop this video over here and give this a thought on your own. Okay, so this is the question, and it's helpful to sort of think about these things as you study them, because that helps you get a better insight into what we are dealing with. So I'll continue. I'll give the answer, but if you like, you can stop the video and mull over it yourselves. Okay. Now, the first thing, can regression problems be formulated as classification problems? The answer is no, because as I said earlier, you would need a very large number of buckets or categories. Well, of course, depending upon what accuracies you're looking for, and the dynamic range of the dependent variables. But you would be looking at a large number of categories. However, and secondly, in a classification problem, when you want to solve a classification problem, you typically need training data for each of the buckets. So you could potentially imagine a situation where you would require a humongous amount of training data if you formulated a regression problem as a classification problem. Okay, that's number one. Number two, there is an even deeper reason. Okay, in classification, there is no concept of adjacency or any sort of relation between buckets. Okay, this is very important to understand. The buckets are distinct, they are sort of not related with each other, and neither are they sort of adjacent to each other or near each other. There is no concept of nearness of buckets. Okay, so the buckets or categories in a classification problem are distinct. Okay, however, in a regression problem, even if you sort of on the dynamic range or the scale of the output variable, if you defined small buckets, small categories, there would be an idea of adjacency. And when you solve regression problems, this idea of adjacency, the fact that values are continuous, they take continuous values, is exploited to come up with better solutions. Okay, so therefore regression and classification are to be treated as two distinct categories of problems. The other way, can classification problem always be formulated as a regression problem? Well, the answer is no, because I gave you one example of value of the stock price and predicting the category invest or don't invest. But there are numerous classification problems where such a continuous variable cannot be defined. For example, right here in front of you, what continuous variable can you define to sort of describe the attire of a person, right? So that's the issue. So bottom line, these are to be treated as two distinct categories of problems, and although some of the ideas may be common to the two categories, the solutions to the two categories of the problems are distinct, okay, are different. So while there is an overlap, they are essentially different. These are two different classes of problems. Okay. So with that out of the way, let us now proceed. Okay. As I said, the focus of this lecture is going to be on linear regression, which is a special case of the generic regression problem. Okay. So what is linear regression? In linear regression, based on the training data, we create a linear model. To best estimate or predict the output for a test input. Okay. So in the regression problem, I said, in the general regression problem, I said that we need to create a model that mimics the input-output behavior on the training data, and it can therefore best estimate the output for a test input. In case of linear regression, in the specific case of linear regression, the model just happens to be a linear model. Okay, so we will talk about what a linear model is, but a linear regression deals with creating linear models to model the input-output characteristics of the training data and thereby predict the output for a given test input. Okay, so that is linear regression. Let us just consider a simple example of, just take one variable, one independent variable and one output variable. So years of experience is the independent variable and salary is the dependent variable. And this is what your training data looks like, right? This is what your training data looks like. Suppose you were to plot this training data on a graph, okay? So here, why the years of experience is the independent variable, independent because it can select independent values, and your dependent variable has been plotted on the y-axis, which is the salary. Okay, and these points that you see here are individuals whose years of experience and salary have been drawn on this graph. So each point represents one individual. So for example, this individual had a particular years of experience and he had a corresponding salary, so on and so forth, right? So that is what this graph is. What we want to do is come up with a linear model. Okay, a linear model in two dimensions. One independent variable and one dependent variable is a straight line. So you want to see if you can come up with a straight line that captures the relationship, broadly speaking, between years of experience and the salary. That captures the relationship between the independent variable and the dependent variable, right? So for example, is this line a good representation of that relationship? Okay, now in this particular case of one independent variable, what you have here, a linear model is basically the equation of a line y equal to mx plus c. Here, instead of y, I am using the dependent variable salary. On the x-axis, you have years of experience. M is the slope of the line and S0 is the y-intercept. Okay, so this is the equation of a straight line, and this is what a linear model looks like in the case of one independent variable and one dependent variable. Okay, So if you wanted to nail down this particular model, what are the parameters of this model? The parameters of this model are m, which is the slope of the line, and the y-intercept s0. Okay, so if you define m and s0, you are uniquely going to define this line, s and y being the variables, right? And then if you are given a value of y, once you have defined this line, once you have the values of m and s0, suppose you are told the years of experience of a particular person, you would be able to estimate the salary of that person using this equation, using this linear model. Okay, so the linear model is basically an effort to fit a straight line in the case of a single independent variable. A linear model, in the case of two independent variables, you would try to fit a plane. In the case of more independent variables, you are going to be speaking of hyperplanes. Okay, but this is an example in essentially in the case of one independent variable. Okay. Just an aside, when people see graphs like these, I mean, one thing that comes to their mind, it came to my mind also the first time around, was, can you have 2 points? I mean, is this valid training data? Can you have 2 points with the same y and different s? Because, I mean, how does that work? Well, the answer to that question is yes. The answer to that question is yes. This should not alarm you, because clearly in life you could have two people with exactly the same years of experience but with different salaries, right? So this is not invalid training data. This is perfectly valid training data, and you need to get used to the idea of training data, or the idea of scenarios where the values of independent variables are exactly identical, but the value of the dependent variable differs. Okay, so that is what that's the point I wanted to make as an aside. So this is linear regression. We are going to find this linear model. Now clearly, I mean, I have drawn some more lines over here. The green line, the brown line would differ from the blue line in terms of the variables m and s0, right? Now if you were to sort of take just one line, this intercept, this s0, what is s0? S0 is the y-intercept, s0, right, in this equation. And what is the significance of s0? S0 is the salary of an individual who has 0 years of experience. Obviously, it's not the case that if somebody has 0 years of experience, you pay him 0 rupees, right? I mean, you still give him some salary, and that is the y-intercept over here. That is the y-intercept over here. That's the salary when years of experience are 0. That's S0 in this equation. So the significance of the constant in a linear model is the value of the dependent variable when all the independent variables are 0. Okay? Great. Let's move on. Okay, here are some examples. Again, some points plotted here, and a straight line was sought to be established. I mean, we said, if let's model this data. Let's model this data with a linear model, and somebody came up with this nice line that more or less passes through these points. Okay. Now, in the situations where there is exactly one independent variable, the category of problems are called univariate problems. It's just terminology. Univariate means one independent variable. Okay, you could think of applications, your marketing budget and the marketing leads, right? I mean, you would expect that your sales leads would go up perhaps linearly as you increase the marketing budget. Or sales to price elasticity. You could imagine that the sales would go down as you price your product higher and higher, and perhaps there is a linear relationship between the volume, the sales volumes, and the price at which you price your product. if you have two or more independent variables, those problems are called multivariate problems. Okay, terminology. For example, assessing risk for insurance. Now, if you are assessing risk for insurance, if you want to sort of estimate the insurance premium for a particular individual, you would typically have variables like the person's age, maybe perhaps where he lives, how many accidents he has been in the past, how many times he has defaulted, his salary, whatever. So you would potentially have multiple independent variables, and that category of problems is known as multivariate. Okay. Now, of course, in a multivariate problem, if you just picked one independent variable, that problem would turn into a univariate problem, right? So that's the way to think about this. The number of independent variables you choose is up to you. Generally, the quality of your answers becomes better and better as you choose more variables, generally speaking. We'll talk about that. But how many variables to take, independent variables to take, is up to you. Okay, that's number one. Number two, can every problem be configured as a linear regression problem? Well, yes. I mean, you can always sort of try to draw a line, and it may not do a good job if your data, if the relationship is not linear, right? So that's simply what's going to happen. Anyway, let's proceed. So these are some of the examples. Next point. Why linear, right? Why linear? Is linear too restrictive? I mean, we asked this question when we were looking at binary linear classification as well. And the answer is sort of similar, okay. Solution can be found for the linear regression problem. Okay, so this is extremely important. You want to begin by dealing with problems whose solution you can find. Okay, because that then becomes a starting point for you to start building more and more complex models. So the fact that a nice, elegant solution can be found for a linear regression problem is an important factor for studying this category of problems. And then, of course, you sort of build on it, like I said. But there is more. Here is a relationship between a independent variable x and a dependent variable y. Okay. Can this problem be configured as a linear regression problem? Okay, can it be configured? You can think about it for a minute, stopping the video, but I'll go ahead and give the answer. Well, if you looked at this a little closely, what you would realize is sort of if we broke this graph into two pieces, okay, for values of x that are less than this x1, for example, in this range and in this range, here clearly it seems that the relationship is linear, right? Here clearly it looks like the relationship is linear. Sorry, pardon that line, right? Here it doesn't look to be linear immediately, but what this does look like is a parabola. So for example, in this range of x, if you were to sort of write this equation as y equal to a x minus b square plus c, right? That could perhaps represent this parabola, right? And then if you did a transformation, on x, whereby you defined a new variable x prime, which was equal to x minus b square, if this was your new variable, you would have a linear relationship in this part as well, right? You would have a linear relationship in this part as well. What I'm trying to say, therefore, is that you have a few tricks up your sleeve in any case. you can transform the independent variable. This is one trick that we used over here. Since x is an independent variable, you can transform it and see if that helps you get to linearity. And the second thing is piecewise linear, where you break the problem into two separate problems and deal with the two separate problems separately. So if the value of x is less than this x1 over here, you deal with this model, and if the value of x is greater than x1, you deal with this model. These are two completely different linear regression models. Okay, so bottom line is, even if you were to be confronted with something that looks like this, you could perhaps play some tricks and use the ideas from linear regression, use the solution from linear regression to sort of build a model. Okay, so that's the reason why it's worthwhile studying linear regression. Okay, so let's get into the woods now. What is linear regression? What's a linear model? As we saw earlier, a linear model essentially means that your output y, is a linear combination of your inputs. A linear combination of your inputs. Okay, so y equal to w1 x1, w2 x2, w3 x3, etc. Values of w1, w2, w3, etc. w1, w2, w3, etc. are the parameters of your model. These are the parameters of your model. Okay, parameters of your model, right? And their values are in your control. Those are the values that you control. And there is also the constant w0, which is multiplied with 1. Okay, so if you had n independent variables, your model has n plus 1 parameters. Let's keep that in mind. The model has n plus 1 parameters if you have n independent variables. Okay, so when I say n independent variables, x1, x2, x3, x4, xn, etc., what I mean, just to recap, is that for these variables, for a particular training point or for a particular test point, you would be given the numerical values of these. You would be given the numerical values of these variables, and in the training data, of course, you would be given the corresponding output as well, right? So you would be given the corresponding output as well, and in your model, you could multiply those values by the weights. You could multiply the values by the weights to get the output y. Okay, the output returned by your model. Okay, so exactly what I said, weights, when I talked about weights are the variables whose values we have to determine. Those are the characteristics of the model. They define your model, right? And as you can see in this linear combination, the sign and magnitude of the weights indicate the nature and strength of influence. Okay, so for example, if the dynamic range of these variables, the dynamic range of variables x1, x2, x3, etc. was roughly similar, then the value of the weight for the variable, for the independent variable which has the maximum influence is going to be higher. So it is going to be weighted the highest. Okay. Similarly, the weight for the independent variable that makes only a slight difference to the final answer is going to be small. The weight for the independent variable which has a strong negative influence meaning its value has a disproportionately negative influence on the output. In that case, that weight is going to be a negative value with a large magnitude. Okay, so the sign and the strength of influence, the sign and the magnitude of the weights indicates the nature and strength of the influence of each of these variables on the final answer. Okay, and like I said, if you had n independent weights, if you had n independent variables, you would have n plus 1 weights. Okay, so moving on. Okay, now I'm going to introduce some vector notation. Okay, so this was the linear model with the independent variables and the dependent variable, right? And we are going to introduce some vector notation. Okay, um, I like to sort of teach linear regression using exclusively vector notation, and I'll show you why. It makes the solution extremely elegant is one thing, but it sort of also gets you familiar with the idea of using vectors and matrices, and that is going to be useful for us for subsequent lectures. Okay, so let's start introducing some vector notation. We said Y was a linear combination of the input variables where each input variable was being defined was being multiplied by the corresponding weight. Okay, now this thing can also be written this way in terms of vectors, right? So this is the vector W. This is a vector W. I'm going to use sort of bold font for vectors. This is the vector W of weights, and this is the vector of independent variables or inputs, right? Now the first value here is going to be 1 because as you can see W0 gets multiplied by 1, and then if you remember how vector multiplication works, this is essentially W0 plus W1 into X1 plus W2 into X2 plus Wn into Xn, right? So this you understand the vector notation. So this is the linear model. The vector W are the parameters of the linear model, and this is the input vector, and the input vector takes different values for different inputs, right? Whether these are training points or the test points. Okay. In vector notation, like I said, we are going to be using bold font for vectors. I'm going to write Y is equal to W transpose X. Why W transpose X? Because vectors are typically considered to be sort of column vectors. So W would look like this actually, W0, W1, Wn. And when you turn it around and turn it into a row vector, it becomes, you essentially transpose it, and therefore the notation that is commonly used is Y equal to W transpose X, right? So W is a vector, X is a vector, and Y is a scalar. Scalar means it's just one quantity. So this is the vector notation. Okay then, let us therefore formulate the linear regression problem. Okay, formulate in the sense what exactly is it that we are going to try to do here, right? Okay. So here is what you have. You have input vectors x1, x2, x3 up to xm, m being the total number of points in your training set. So these are the m inputs corresponding to your training set. Each of these is a vector. Each of these is a vector of size n, okay, and comprises the values of the independent variables for that training input, right? So m training points, x1 through xn, okay. For each of these training points, you also have an observed output. We call that y hat, okay. So y hat 1 is the observed output when the vector x1 was the input, so on and so forth. So for each of these m training points, you have m outputs that you observed, which you got in your training data. If you constructed a linear model with some values of W, and if you gave these vectors x1, x2, x3, etc. as inputs to that linear model, let us say your observed or your computed, not observed, your computed outputs were y1, y2, y3 and so on and so forth. Okay, this is ym subscript, right? So the y hats are the observed values of y. whereas the simple y's without the hats are the computed values of y for each of these points in the training data, right? What we have to do is find the linear model. In other words, find the values of these w's, the coefficients or the weights of this model that reduce the deviation between y hat and y as much as possible. Okay, so you would like your y's and the y hats to be as close as possible to each other, and your task is to find the w's, the weights, so that indeed for the training points they are as close to each other as possible. Okay, if you were to look at these in a diagram, what we are essentially saying is that if these black points were your training data, you want to construct a hyperplane. That sort of runs as close to these training points as much as possible. Okay, now we will formulate this mathematically, what it means to say that the deviation should be as less as possible, as close as possible. We will write some mathematical formulas for that, but essentially what you're trying to do is determine this hyperplane that runs as close to as possible to the training points, right? So that is what you want to determine. You want to determine the coefficients, the w's, which in other words is the same thing as determining this hyperplane. Okay, because this hyperplane is in fact defined by this equation. This is the equation of that hyperplane. Okay, now it's time to actually mathematically formulate the idea of, you know, reducing the distance between the y hats and y's and so on. So let's mathematically formulate that. Once again, I've written here the fact that the y hats are the observed values and the y's are the computed values, right? So this is what we have. And if you were to sort of define our favorite mean square error metric, right? Mean square error metric, which we have looked at in the past, it would look something like this, right? This is your mean square error, right? And this is a good metric to consider and to aim for minimizing, right? Because what this is doing is I runs from 1 to m. It runs over all the points in the training data. For each of the points in the training data, you find the difference between y and y hat, okay, and take its square, and finally divide the whole thing by 1 over m. This, we have seen this sort of a mean square error in one of our earlier lectures. So we will continue to use this as a metric because it's a good one, and it essentially captures what we want to do, because overall we want to reduce the error between the observations and the computed y's, right? So this is the metric that we are going to be using for getting the best weights. Okay. Now, if you were to look at it in a diagram, what we are going to be doing is essentially this. I'm showing this to you in just in 2 dimensions, where there is a single independent variable. Y is the dependent variable, right? And the black dots here are your observed values of y for each of these values of x, right? Now, the difference between your plane, okay, suppose you were to come up with this this hyperplane in 2 dimensions is just a line which I have drawn. The difference between the computed value of y, okay, and the observed value of y is called the residual. Okay, this is called the residual. Okay, so yi minus yi hat is called the residual, and you are essentially finding the sum of squares of the residuals when you compute the mean square error, right? So this is the residual for each of the points. For each of the points in the training data, you are going to find the residual, the difference in the value of y, observed value, and the computed value. Since the plane is what the line is what you computed, or the line is what your model is, this difference is essentially the residual, and you are finding the sum of the squares of the residuals, right, for each of the points. That's what the mean square error is. Now, just want to, it's clear from this diagram, but I just want to point it out once again. You're not looking, I mean, your residual is not the distance of the point from the line. Okay, so it's not the perpendicular distance. It is not this. Sorry, let me draw this a little bit better. It is not this. Okay, it's not this. It's not the perpendicular distance. It is simply the distances between the two y's, the values of y as observed and the value of y as computed, right? So this would be y hat and this would be y, and that's the difference. That is the mean square error, right? The residual could be either positive or negative depending upon which side of your model the observations lie, right? So we are going to be using the mean square error as an error metric, and our job is going to be to minimize the mean square error. Okay, I want to spend a minute talking about these two quantities m and n, okay, because I don't want us to sort of overlook what these exactly mean. We need to remember at all times what m and m really are. Okay, so m is the number of points that we have in our training set. Okay, so total number of points in your training set is m. The vectors x run from x1, x2, x3. These are all each of them are vectors, and you have m of these. N is the number of independent variables that you have. Okay, n is the number of independent variables that you have, and therefore the size of each of these, the size of each of the x's is n plus 1, because you remember in each of these x's we appended a 1 right at the top because we had n plus 1 weights, right? So n plus 1 is the dimension of each of these vectors x, n is the number of independent variables, and m is the number of points in your training data. So these numbers could be anything. I mean, depending upon how complicated your model was, n could be more, and depending upon how much data you gathered, m would depend on that. I mean, the more data you gather for your training, higher is the m, right? So these are the two quantities that we are talking about. Okay, a few quick observations, right? Generally, if m is equal to n plus 1, generally, you can get a solution with zero mean square error. Okay, what do I mean? Simply in, let's say, in 3 dimensions where you had 2 independent variables and 1 dependent variable. 2 independent variables, I said 2 independent variables. 2 independent variables would be these, and the dependent variable is this one. And with n equal to 2, if I had 3 points, in this 3-dimensional space, in general, given any 3 points, I can find a hyperplane that passes through each of these 3, right? For example, in 2 dimensions, if I am given 2 points, I can always find a line that passes through both of those points. So if I can find a hyperplane in 3 dimensions, which passes through all of these points, right, I essentially get a model that gives me zero mean square error on my training data, because there were only 3 points in this case, right? The reason I say generally is because we assume that the points don't fall on top of each other, right? In which case we get an infinite number of solutions with zero MSE. So when m is less than n plus 1, you would get an infinite number of solutions with zero MSE. In this case, for example, in 3 dimensions, if you were given 2 points, you can find an infinite number of planes that pass through those 2 points, right? So, or in the case of just a plane, if you were given 1 point, right, m less than n plus 1, you would be able to find an infinite number of lines that pass, the infinite number of lines that pass through this 1 point, right? So each of those would represent a solution with zero MSE. And finally, in the most common case, When m is greater than n plus 1, which covers the practical scenarios that we will run into, you look for an optimal solution, because you will not get a solution with 0 MSE on your training data, right? In other words, it's going to be not possible in general to find a hyperplane in 3 dimensions that passes through 4 points, right? I mean, it's not possible to find a plane that passes through 4 points in 3 dimensions, and unless they satisfy, unless it's a very special case. So in those cases, when m is greater than n, which is most of the practical scenarios, you are looking for an optimal solution which will have some mean square error. Okay, the mean square error is unlikely to be 0. Okay. So, I mean, when I was looking at this, like I said, I mean, I had my own questions. One of the questions that came to my mind was, why can't you just work with m equal to n plus 1? So, for example, if you have 2 independent variables, why not just take 3 points from training data and find an hyperplane with 0 MSE? The problem would be very easy to solve, because there is a solution for finding the equation of a plane passing through 3 points. I mean, you know how to do it, right, from geometry. So why not just work with m equal to n plus 1? Okay. Well, the answer is obvious. I mean, your gut feeling tells you that m may just be too small, right? I mean, the idea of working with just 2 training points for a problem that has 1 independent variable, or working with 3 training points for a problem that has 2 independent variables, it just appears, it doesn't appear like something that you should be doing. I mean, that just seems like very little training data. Intuitively, that's your sense, right? Well, if that is the case, how much training data do you really need, right? I mean, right now we are not going to answer this question. The reason I'm asking this question right now is because after we are done with linear regression, we are going to jump into the theory of learning. Okay, we'll do a couple of lectures or more on theory of learning, and we will essentially address this exact problem. I mean, how much training data do we need? This is one of the things that we will address there. Okay. So while I don't have an answer to this question in this lecture right now, I think intuitively we all agree that m equal to n plus 1 is just going to be too less. I mean, it just, something tells us, our gut feel is that m simply should not be used, because those could be outliers, or that's just too little data. Okay. So I want to leave it at that. I want you to keep this question at the back of our minds when we proceed to lectures further down this series. How much training data do we need? Okay, how much training data do we need? Okay, let's get back to solving the linear regression problem that we formulated. Okay, the linear regression problem is special. Okay, it's special because there are 2 ways to solve it. Okay, one solution is what we call a closed form solution. Okay, linear regression problem is one of those rare problems for which a closed form solution exists. Okay, a closed form solution exists. A closed form solution means you can actually write the values of weight should be equal to so and so. Okay, so that's a closed form solution. And the other type of solution that can be that can be used for solving the linear regression problem is an optimization based solution, somewhat similar to what we did in the case of classifier. Okay, so iterative optimization solutions are always iterative. That is the second way to solve the linear regression problem. Okay, so there are 2 ways to solve the linear regression problem. We will cover both of them in this lecture, and let's see what these are. I mean, both of them essentially give the same answer, but you may want to prefer one approach over the other for specific scenarios or for specific type of problems that you have. Okay, so it's a good idea to learn both of these ways of solving the linear regression problem. Okay, we will begin with the closed form solution because it's elegant, it's nice. I mean, it exists. Like I said, linear regression is one of those, few problems that actually have a closed form solution. And they are also known as normal equations, right? We introduced the vector notation earlier in our in this lecture. We said that we would be using the vector notation. And while we discuss the solution to the normal equations, the closed form solution, you will see why I said that we should use the vector notation. I mean, of course, it makes the solution very elegant. Okay, it makes the solution very elegant because you don't have to deal with summations, double summations, and so on. And the solution becomes very, very understandable and elegant. Okay, it becomes short, easy to understand, and so on and so forth. And since these are educational lectures, we might as well learn a few things, start getting used to the vector notation, which we haven't used so far. Okay, so we are going to define these two vectors, y and y hat. Y and y hat are the vectors of the outputs. Y is the vector of values of y that are computed from your linear model for certain values of w. Okay, and y hat is the vector of your observed dependent variable, right? So these are the two vectors that we have. And your mean square error, which we said was y1 summation, we said it was equal to 1 over m summation, okay, it's right here, yi minus yi hat the whole square. This was your mean square error, right? And this mean square error in vector notation can be written simply as 1 over m vector y minus y hat transpose into y minus y hat. Okay. You know how vector multiplication works. You transpose this vector with that and multiply it with itself. This is what you are going to get, right? Okay. So your MSE, your mean square error in terms of in your vector notation is going to be this. Okay, I hope you don't require me to show that this is equal to this. I mean, it would be a good exercise for you to actually write down the values of y and y hat, subtract the two vectors from each other, transpose the vector and multiply it with itself. You are going to get this. I guess I can, it's pretty straightforward. I can leave that as an example to be done, as an exercise. Okay, some more notations. Your vector y is actually the multiplication of this matrix with the weights, right? I mean, why do I say that? You know that your yi, okay, so the values of y that you get from your model are equal to w0 plus w1 x1 plus w2 x2 and so on and so forth, right? This is what your y computed from your model is. Now for each of these, for each of the points in the training data, like we said, we would have the values of the independent variables, right? And when these values of these independent variables are multiplied by the weights, you are going to get the output returned by the model, right? For each of these points, actually, W0 is multiplied by 1, which means that all of these x's here are actually 1. Okay, so x10, x20, x30, xm0 are all 1, and x11 is essentially the value of the independent variable 1 in training point 1. x12 is the value of the independent variable 2 in training point 1, and so on and so forth. Similarly, let's say x31 is the value of the independent variable 1 in training point 3, and so on and so forth. And because you have m training points, xmn is the value of the nth independent variable in your mth training point, right? So this is what this notation is. And I'm going to simply write this as y equal to xw. So y is the vector of answers returned by our model, w is the vector of the weights, and x is this matrix. Okay, x is the matrix of values of independent variables for each of the points in the training data. And the dimension of x is, of course, it has m rows and it has n plus 1 columns, right? The matrix X has n plus 1 columns. The vector W has n plus 1 elements. So this matrix vector multiplication works. And of course, there are going to be m outputs, and m is the dimension of this vector Y, right? So this is the equation we have written down, and we have just written this down as Y equal to vector X times W. Okay, so Y equal to XW. If I plug y equal to xw in the equation of my mean square error, what I get is, this was the equation of your mean square error. I just plugged in y equal to xw and I get my mean square error is equal to this. Okay, all I have done is plugged in xw for y. Okay, where x is this vector and w is, of course, the vector of weights. So I'm gradually sort of, like I said, moving to the vector notation as far as MSE is concerned. Now the MSE, I will just go back. The MSE is, the mean square error is a quantity. It's a quantity, it's a scalar, it's a number, and it is a function of multiple variables. The multiple variables being the weights. Okay, so the MSE is a function of n plus 1 variables, right? The variables being the weights. There are n plus 1 weights. These are the variables, and the MSE is a function, okay, whose value is a scalar number, and its value depends on n plus 1 variables. So it's a function of n plus 1 variables, the n plus 1 weights. Sort of re-emphasizing this again and again so that you are not confused. How do you optimize a function of multiple variables? Let's go back to our calculus, right? To find the minima or the maxima of a function of multiple variables, let's just take the example of 2 dimensions which you may be familiar with. You find the point where the gradient is a 0 vector. Okay, where the gradient is a 0 vector. So let us see what the gradient is, right? If you had a function in 2 dimensions, your gradient is typically defined by this inverted delta. Your gradient of the function f is basically the vector of partial derivatives with respect to each of the variables. So if it's a function of 2 variables x and y, your gradient vector is the derivative of x with respect to y, derivative of x with respect to x, derivative of x with respect to y, and so on. If you had multiple, you would sort of have a longer and longer vector, right? So the gradient of a function is a vector whose elements are the partial derivatives of that function with respect to each of the independent variables, right? Okay. And we said that the minima, an extrema, maxima, or a minima would be the point where the gradient is a 0 vector. So gradient is a 0 vector. I am going to indicate a 0 vector by writing a 0 with a bar on top. What that means is that each of these partial derivatives has to be 0. Each of these partial derivatives has to be 0 because why? Because let's say you are at a minimum, your value of the function would not be changing in any direction at that one particular point, right? So along all the independent axes that you have, the value of the function would not be changing along any of those directions, and therefore the partial derivatives of the function at that point, evaluated at that point, would be 0, right? And therefore this gradient vector would be 0 at that particular point. So that is the way you find the minima or a maxima. We are interested in the minima in this case because we are trying to minimize the mean square error. And therefore the minimization of a function of multiple variables happens when its gradient vector becomes a 0 vector, right? So we are going to remember that. We are going to remember that. This is very similar to the case of one dimension. I mean, in the case of one dimension, you know that, to find the minima, you would equate the derivative, you would compute the derivative and equate it to 0, solve it for the point where, it is 0, and that would be a minima, right? Or a maxima. That's exactly what we are doing. But in the case of multiple dimensions, you have to do exactly the same thing along all the directions, and which is why you end up having a gradient, a vector, instead of a single quantity. Okay, so that is exactly what we have to do now, right? I mean, we have the mean square error, which is a function of multiple variables. I have colored these weights in orange just so that, they are very obvious to you. This mean square error is a function of multiple variables, which are the weights, and it is defined in this way. Okay, this is what the function is. Function of the n plus 1 weights, right? And the way we are going to minimize this mean square error is to find the gradient, and equate it to 0, okay? And when we find the gradient equated to 0, that would lead us to the best values of w, or rather the best value of this vector w, right? So that is exactly what we are going to do. It's an idea that we are familiar with. Compute the gradient of the function, equate it to a 0 vector, okay, and that tells you what the best values of w are. Okay. Because we have chosen to go the route of doing all of this in vector matrix notation, I am going to introduce a few useful identities. Okay, a few useful identities. Firstly, I mean, some of these may be familiar to you. If they are not, I'll tell you how they come about. But A plus B transpose is equal to A transpose plus B transpose. Okay, this is one identity number 1. Number 2, AB transpose is B transpose A transpose. So the sequence of the matrices changes when you sort of take their transpose. Okay, so AB transpose is B transpose A transpose, right? Number 3, gradient of C plus D, okay, gradient of sum of two quantities is the gradient of the first quantity plus gradient of the second quantity. Again, this you may already know. Number 4, important. Gradient with respect to W. Okay, I'm sort of indicating a small w here so that you understand what the variable is with respect to which you are going to be doing the differentiations, right? Gradient of W transpose A, is equal to gradient of A transpose W, and it is simply the vector A. Okay, so here A and W are vectors. W transpose A transpose W, both of their gradients are identical, and it is simply the vector A. Okay, how do you prove this? You can prove this simply by choosing values of W and A. I mean W1, W2, W3, just sort of expand W transpose A or A transpose W, and then differentiate the result with respect to each of the with W0, W1, W3, etc. Put them in the form of a vector and you will get A. Okay. So this is identity number 4 that we are going to be using. Number 5, very useful. Gradient with respect to W of W transpose AW is equal to A plus A transpose times W. Okay, so look at it for a second. W is a vector. W is a vector of the variables with respect to which we are going to find the gradient. A is a matrix. A is a matrix. In particular, it's a square matrix. Why? I mean, in this identity, it's clear that it's a square matrix, because the number of rows in A equals number of elements in W, and the number of columns in A also equals the number of elements in W, which is why this vector matrix multiplication would be okay, right? I mean, this would be true only if A is a square matrix. Square matrix means number of rows equal to number of columns for A. For any given A, which is a square matrix, the gradient of W transpose AW is equal to A plus A transpose multiplied by W. Okay. So A plus A transpose, again A plus A transpose, you can add two matrices only if their sizes are identical. And if I am writing A plus A transpose here clearly means that this applies only if A is a square matrix, right? So this identity is also extremely important, and it is, again, I mean, the proof is not complicated. It only relies on you sort of, you know, taking taking an arbitrary W, putting in values W0, W1, Wn, taking A with A0, A00, A01, etc. I mean, writing a general matrix A, computing this thing, right? Blowing up this thing by actually doing the multiplication, then taking the gradient of that quantity and rearranging the terms and writing it in this way. Okay, so the proof is not terribly complicated in the sense it does not involve any new principles. It is just a matter of writing this thing out, expanding it and rearranging the terms. And I'll again therefore leave it as an exercise, but if you can't do it, since it's important and we are going to be using this identity, I'll also put a link to this proof in the description of this video, right? So these identities are important, and you may want to turn the page to these identities while we go about finding our closed form solution. Okay, so that's just what I wanted to put out in advance, and by giving you these identities upfront, it will allow you to familiarize yourselves with these identities, and once you sort of accept these, some of these proofs, for example, particularly the last one, you can look at the proof later if you can't expand and sort of prove it yourselves. But for the moment, assume that it is true because you have a link to that proof. So let's remember these identities for now. Okay. Okay, so with those identities in hand, let us begin to find the closed form solution for the linear regression problem. Okay, that's what we want to do. This is going to be a slightly busy slide. I told you that the vector notations would make things elegant, and you will see what I am talking about when you go over this slide. Having said that, this is a slightly mathematical slide, so you may need to focus on what's on it. Okay, right? So we saw earlier that the mean square error was essentially 1 over m xw minus y hat transpose multiplied by xw minus y hat. Okay, we saw this in an earlier slide, so this is nothing new. This is what our mean square error is. Okay, the first thing that we are going to do is basically simplify this thing, okay, by multiplying it out. And here I take the transpose. So x w transpose becomes w transpose x transpose minus y hat transpose, and this gets multiplied by the same thing right here, right? So this is the mean square error, simplified. I have dropped the 1 over m because remember what we said, we would find the gradient and set it equal to 0, and at that time your m is anyway going to vanish. I am going to therefore drop the m so as not to clutter these equations. Okay, the m has been dropped only to not clutter these equations. There is no other reason, technical reason for dropping m. Okay, so let us work through these simplifications. Now I am going to multiply these two brackets, and what you get is w transpose x transpose multiplied by xw. That's the first term right here. Then you get w transpose x transpose multiplied by y hat. That's the second term, minus sign. Third term is the third term is y hat transpose multiplied by xw, right? That's right here. And finally y hat transpose y hat, right? So you just blew this thing up by multiplying it out and sort of expanding it. Okay. So this is your mean square error. Now it is time to take the gradient, compute the gradient of this mean square error with respect to the weight vector w. Okay. So let's carefully look at these equations and see how they simplify. Okay. So when I take the gradient of the mean square error, remember we said that gradient of a plus b is gradient of a plus gradient of b. That is exactly what we have done. We have taken the gradient separately of each of these four terms above. Okay. All of these quantities whose gradients you are taking, are scalar quantities. Okay. You take a gradient of a scalar quantity, and the gradient itself, the result, the gradient itself is going to be a vector. Let's remind ourselves of that once again. So these things that I have circled, each of these terms is actually a scalar. Okay. So gradient of the mean square error is the summation of the gradient of these four terms right here. Okay. Now we use the identities that we talked about on the previous slide, right? So gradient of w transpose x xw. Okay. This here you use the identity. Here you use the identity for gradient of w transpose AW, right? Identity number 5. And here A is x transpose x. And x transpose x is always a square matrix, right? So this fits into the requirements of our identity number 5, and therefore we have written it out as, you remember what this was, the gradient of this was a plus a transpose times w, right? So that's exactly what I have done here. And this being a plus a transpose is x transpose x plus x transpose x transpose w. The next term is, here we use identity number 4, where we said we want to compute the gradient of WA, right? Vector multiplication of vector W with a constant vector A, right? This is constant with respect to W, and therefore identity number 4 is being used over here. So what we have over here is simply x transpose y hat. Same identity being used here, and I get x transpose y hat, right? So this is what I have. And finally, the last term here, this is constant with respect to w, because these are not the computed y's, these are the observed y's in the training data, and therefore this term is constant with respect to w. This term is constant with respect to w, and therefore its gradient is 0. So there is no fourth term over here. Now the last simplification right here, x transpose x, the whole transpose, is simply x transpose x, okay, which is exactly this, right? And here we used identity number 2 from the previous slide, and therefore simplifying this, these two terms are identical. This and this is identical. So what we have is 2 times X transpose X W minus 2 times X transpose Y hat, and I have reinserted the M which we dropped over here, right? M is a constant and therefore it just comes out as a part of the gradient. I didn't carry that M all along with me just so as not to clutter, but I reinserted it right here, and this is the gradient of your mean square error with respect to the weights W, right? So this may look like a particularly sort of complicated slide with the equations and so on, but actually these steps are dead simple. You can go over them once again if you like, and I can tell you that there are multiple ways in which you can compute the closed form equation. All of them essentially do the same thing, but the vector notation by far is the simplest and the most elegant approach to solving this and obtaining your optimum W. Okay, so I hope this also gives you an opportunity to get familiar with gradients and vector matrix multiplications, notations, etc., etc. That's the most important thing. Okay, so for minima, for computing the minima, remember we said that we would equate the gradient to a zero vector. Okay, and this is the gradient from our earlier slide. This is the gradient from the earlier slide. We have equated it to the zero vector. Okay, and we can therefore solve this for W. We can solve this for W, right? X transpose X2, 1 over M goes away. X transpose XW is equal to X transpose Y hat. Okay, and if I multiply both sides of this equation by the inverse of this matrix, I get W, the vector of weights, is equal to X transpose X inverse multiplied by X transpose Y hat. Okay, so this very, very important result, it's a nice one. It's one of those rare cases where you actually find a closed form solution for a problem. Linear regression is one of those cases where you can find a closed form solution, like I said, and your ideal W's, the ideal weights in your linear model are simply given by this equation. The right hand side are things that you know. Okay, so X is the matrix that we saw earlier. It was the matrix of the inputs for the training points, right? So X is a known quantity. It entirely comprises of the inputs for the training data. Y hat were the observations in your training data of the output, right? So the right hand side is completely known. You only have to solve this thing to get the ideal values of W, right? Okay, so this is the closed form solution for finding the best weights of the linear model that minimize the mean square error. Great. Let's now move on to the optimization solution where we are going to use the gradient descent. But let me step back a bit. I mean, this equation looks really nice, right? I mean, like I said, it can be evaluated. Remember the size of the matrix X was M into N plus 1, right? So it had N plus 1 columns, right? And therefore you have this matrix X transpose X, which is of size. The size of X transpose X is N plus 1 multiplied by N plus 1, where N is the number of your independent variables, right? So you are inverting a matrix of size N plus 1 by N plus 1. So if you had, let's say 5, 10, 50, 100 independent variables, these are the different parameters that you observe. That would be the size of the matrix that you are trying to invert, right? Matrix inversions are generally considered to be computationally intensive, okay, and as the size of the matrix grows, you start running into difficulties, computational difficulties in computing the inverses of matrices, okay. Therefore, if the size of the matrix to be inverted starts becoming very, very large, like many thousands of rows, if the number of your independent variables is, let's say, 10,000, you may struggle to invert a matrix of size 10,000 by 10,000, right? So, in those cases, perhaps this closed form solution is not what you're looking for. Okay, you would typically, the computational difficulties of finding an inverse start kicking in when your n starts becoming very large. That really is the motivation for going on to the other way of solving the linear regression problem. So that is a primary motivation for the next approach that we are going to talk about. Gradient descent based optimization solution. Okay. So this is going to be very similar in case you've seen the optimization session that we did for linear classifier. This is going to be similar. Of course, the objective function is a little different, but let us see how this goes, right? Okay, so a quick recap of what the gradient descent algorithm does, right? In the gradient descent algorithm, what we do is we find the gradient of the function. We find the gradient of the function at any given point, wherever you are sitting, okay? And then move in the direction of the negative gradient, okay? Because it's the direction of the steepest descent. So what do I mean by this? Let us say this is your function. Okay, this is the function, two variables for simplicity and being able to sort of visualize. Let us say this is the function and you are sitting at a particular point. Okay, you are sitting at a particular point. Let us say x0, y0. Okay, sorry, you are sitting at this particular point, and what you have to do is you have to find the gradient of this function at this particular point. How do we do that? You know that the gradient is essentially the vector of partial derivatives with respect to each of the variables, right? And once you compute this, now this itself, this quantity, this partial derivative itself is a function of x and y, could be a function of x and y. Similarly, the partial derivative with respect to y could be a function of x and y. And if you are sitting at a point, let us say x0, y0, okay, x0, y0, what you do is you essentially plug in the values of x0 and y0 into this gradient function to compute the gradient at this particular point. Okay, that is how the gradient at a particular point is computed. Fairly simple. Take the gradient and plug in the values of x and y where you are sitting, right? Now, what you then do is the gradient descent algorithm essentially says that the gradient gives you the direction of steepest descent. Direction of steepest descent means the direction in which the value of your function is reducing the fastest. Well, the gradient gives you the direction in which the value of the function is increasing the fastest, and the direction opposite to the gradient is in which it is reducing the fastest. So you have to travel in the direction of the negative gradient, which is the direction in which the value of your function is reducing the fastest. And therefore, what do? You take a small step in the direction of the negative gradient from the point x0, y0. So essentially what you're doing is you're taking a small step to move to a fresh point, let's say x1, y1, let's say call it x1, y1, okay, where this movement is in the direction of the negative gradient, okay. So how do we write that? How do we write that? In the general case, I'm going to write this as you move to a point xk, yk from the point xk minus 1, yk minus 1 by taking a small step in the direction of the negative gradient, and this one is going to be computed at the point k minus 1. So this is going to be computed at the point k minus 1, and you are going to change the values of x and y by a little bit of a small multiple of the gradient here. Okay, so this is the gradient descent algorithm. Okay, of course, you ask the question, what do I mean by a small step size? What exactly is a small step size? And that is related really to the value of this alpha. This parameter alpha goes by several names. It's called the step size, as we called it earlier. It's also called the learning rate. Okay, learning rate. Okay, these are just terminologies, but the learning rate is a parameter that you sort of control, or a parameter that you have in your hand, which you may perhaps need to experiment with various values of, but it is most likely to be a small positive number. Now, whether it is 0.01 or whether it is 0.05 or whether it is 0.2 is up to you. You may actually have to experiment to find the best value of alpha, but it's a small positive number called the step size or the learning rate. Now, after you move to the point x1, y1, you again compute the value of the gradient, evaluate the value of the gradient at this new point by plugging in the values of x1, y1 in the gradient, and then move to the point x2, y2, and so on and so forth, right? So this is the way your iteration goes, right? This is known as gradient descent algorithm. And the hope is that if you keep trying to do this, if you keep trying to take these small sizes, you will eventually end up at the minimal value of the function, right? So that is the philosophy behind gradient descent. The most important takeaway from gradient descent is the fact that you have a parameter here that you need to control called the learning rate. And this is really something that you need to play around with. Okay. Well, I mean, those of you who are familiar with one-dimensional calculus, of course, know that this is just a simple extension to multiple dimensions of what you do in the case of, the single variable. You find the derivative and you either increase or reduce the value of x in the direction where, the function is reducing to sort of go in small steps to the final answer, right? So that's exactly that extension of that familiar case in single dimension to multiple dimensions. Here you have a gradient. So this is the approach that we are going to follow, right? And all that it really requires you to do is to find the gradient of the function that you are trying to minimize. Now, we already did that, right? I mean, in our earlier slides, we already found that the gradient of the mean square error with respect to this weight vector W was this, okay? If you don't remember this, you can turn the pages back. You can go back to the previous slide and take a look and convince yourselves that this is exactly what we had. In the case of the ideal solution, we just simply equated this to 0. Here we are going to be using this gradient to take small steps to eventually iteratively move towards our best solution. Okay. Now what I am going to do is simplify this in a slightly different way. I am going to sort of group x, w together, and therefore what I have is the gradient of the mean square error is really 2 upon m, x transpose comes out, and because this is y, right? Remember, this is y, this is like from a slide a long time ago. This is y, so the gradient is essentially 2 upon m x transpose y minus y hat. Okay, y minus y hat, remember, is essentially the error vector, right? Remember, y minus y hat is You could also call it the vector of residues. So all that is really happening is the gradient of the of the mean square error at a point is x transpose multiplied by the vector of residues, right? And therefore what we are going to do is your new variables, your new w is going to be your old w minus because direction of negative gradient, alpha, which is our step size, learning rate, call what you will, it's a small positive number, multiplied by x transpose times y minus y hat, right? So this I am putting it over here. So this really defines the iterations for you for your gradient descent algorithms. Your new vector of weights is calculated from the old vector of weights by essentially using this formula. And note that y really depends on w's, right? So y has to be calculated using w old, right? And what is y? Y is x times w. It's going to be calculated using y old. So in every iteration, as you go along, this is going to change, and consequently your values of w will be refined further and further. So like I said, y new, let's say y 967 is equal to w 966 minus 2 upon m times alpha x transpose, which does not change from iteration to iteration because it is what you observed in the training data, multiplied by y minus y hat, where y is computed using W966, right? So this is how your iterations go about. And eventually, when do you stop? You stop, like we said in an earlier lecture, you stop when your values of W don't change all that much. I mean, you have essentially converged at that point, right? So when the values of y change by far too little, you can define what too little means. Maybe the values of y change by norm less than 0.0001, whatever. I mean, you can define a threshold, but when you reach a threshold where the values of y are no longer changing significantly is when you stop these iterations. Okay, and when you stop, those values are going to be very close to what you get using the closed form result. So this is our gradient descent optimization solution for linear regression. Okay, want to spend a minute on some of the ideas that we talked about: learning rate, convexity, convergence, and so on and so forth. Remember, we said that in the iterative optimization solution, you move to your new point xk, yk from the point xk minus 1, yk minus 1 by moving in the direction of negative gradient with the gradient, this is 1 k minus 1, where the gradient value is computed at the point k minus 1, right? So by plugging in xk minus 1, yk minus 1, that's what I meant. And alpha, we said, was the learning rate or the step size. Okay. Now, the fact that alpha is a variable in your control is a double-edged sword, right? I mean, why is it a double-edged sword? It's a double-edged sword because if you end up choosing a judicious value of alpha, your algorithm would work very well. But if you did not choose a good value of alpha, you could end up in trouble, right? So that's the reason why you have to, that's the reason why it could be a double-edged sword. Now, what do I mean by a wrong value of alpha? Let us say you are at a point somewhere over here, right? So if you are at a point over here And if you choose a value of alpha, let's say this is the direction you got, right? Let's say this is the direction you got. And instead of taking this step size, let's say you took a step size that looked something like this, and then you calculated the value of alpha and you calculated the value of alpha, you came somewhere over here, you went somewhere over here. I mean, you can imagine a situation where a large value of alpha may actually prevent you from converging towards the ideal solution. And in fact, you could potentially draw curves where you could, essentially get thrown off somewhere outside, right? So you could actually diverge from the solution that you are looking to end up with. So the step size, the value of the step size you choose is an important parameter in your hand that has to be judiciously chosen, right? So on the other hand, if you choose a very small step size, it would simply mean that the number of your iterations would grow and it would take a terribly long time for you to converge, right? So therefore, the value of choosing the right value of alpha becomes so important. And because you don't know what the right value of alpha for your problem is, you essentially end up having to do a little bit of experimentation, right? This sort of an experimentation does not enter the picture in the case of closed form solutions. Okay, convexity convergence. Okay, so how do we, first of all, I've drawn a image over here that has multiple minima, right? So this is one minima, this is another minima. How do we know that in this sort of a problem, we are not going to end up in one minima vis-a-vis the other? Now, why one minima vis-a-vis the other? Why do I raise this point? For example, the value of the mean square error over here may be higher than the value of the mean square error over here. And if you ended up converging at a point which was not the global minimum means the minimum overall for the overall function, you could be in trouble, because then it would depend probably on your starting point where you began these iterations, right? So if you, for example, began your iterations over here, if your x0, y0 was here, you would converge over here. If your x0, y0 was here, you would converge over here, which is the answer that you were looking for, right? So how do we know in the case of the linear regression problem that we have not ended up at a local minimum, we have ended up at a global minimum? Okay, so the answer to that problem, the proof of that is a little bit outside the scope of this lecture, but this is a convex function. Okay, the mean square error that we have computed for the linear regression problem is what is called as a convex function. And in a convex function, there is one minimum, which is the global minimum, where you converge if you do end up converging, right? So the problem of the issue of ending up at a local minimum, which is not the global minimum, does not arise in the case of linear regression problem, right? So your convergence is guaranteed to be at the global minimum because this is a convex function. Okay, the mean square error that you are minimizing is a convex function in the case of mean square error computed for the linear regression problem. Okay, this sort of also goes back to the question that we dealt with: why do we study the linear regression problem? Why make such a big deal out of it? And we said one of the reasons was the fact that a solution can be found, right? I mean, see how important these things are, right? I mean, the fact that you can find a solution where you know that the mean square error function is a convex function, therefore your iterations are going, your gradient descent iterations are going to converge to the global minimum. All of this is so valuable, right? I mean, this is not guaranteed for every optimization problem you pick up, right? And therefore this is good. You can actually find a solution to the linear regression problem, and therefore we begin to study regression problems by first studying the linear regression problem and then building on top of it without losing the good things that we get in the linear regression problem, right? Of course, the other good thing is the closed form solution that we talked about. So these are the reasons why we are studying the linear regression problem in the first case. Okay, let's move on. So what we dealt with here are two ways to solve the linear regression problem. A quick recap of what we did. The closed form solution looked like this. Where the value of the best weights W could essentially be computed by finding the value of this expression on the right hand side. It involves the inversion of a matrix. It involves the inversion of a matrix of size n plus 1 multiplied by n plus 1, okay, where n is the number of independent variables. There are no parameters to tweak, which is a good thing. So you cannot end up choosing a wrong value of a parameter, but you have to deal with this inversion, right? On the other hand, the iterative or the optimization based solution involved selection of a learning rate. I mean, this was the optimization iteration, W new equal to W old minus 2 over m alpha, which is the learning rate of the step size, times x transpose multiplied by the residual, right? So it involves selection of the learning rate, which, like we said, if you made bad choices, you would not converge. And on the other hand, it does work for large n, right? Because there is no inversion, there is no matrix inversion involved, you just keep iterating, right? So I think it's a good idea to sort of stare at these two approaches for a moment, and see exactly how they differ, right? I mean, in the case of the closed form solution, you are directly finding the values of the weights which minimize your mean square error. You are actually finding these out. And in the case of iterations, what you're trying to do is you're sort of trying to take these small steps to move towards the ideal solution, right? That's what you're trying to do. Okay, so these are the two kinds of approaches to keep in mind, and you could use one versus the other. Both are available in scientific libraries if you use tools like Python and commonly used libraries. We'll come to that later. Great. Okay, summary so far. We looked at what linear regression is, right? In this lecture, we looked at what linear regression is. We said that it was essentially constructing a linear model, same thing as identifying a hyperplane in multiple dimensions, which best passes through the points in your training data, right? And then we sort of got busy trying to find the equation of this best hyperplane, the best weights, that is, and we had two approaches to do it. We had the normal equations, which gave us a closed form solution, and we had the iterative solution, which was a gradient descent algorithm, and we saw the trade-offs in either of these two approaches. So that is what we have done so far. So I said summary so far. I typically do summaries at the end of lectures, but now since that we have I've decided to take things up a notch. I'm going to try to keep my explanation of the basic concept simple, but I intend to start challenging you with questions at the end of each lecture. Okay, and these are typically questions that came to my mind when I looked at these ideas for the first time. Maybe you may have these questions. I mean, you may have these same questions in your mind. If you don't have these questions in your mind, it's always a good idea to challenge yourselves with these. So this is what I'm going to start doing. I'm going to start putting out some questions at the end of each lecture, and these are typically questions that came to my mind when I studied these topics, right? So let's move on to the questions. Okay. I asked you 2 questions during the lecture, so this is question number 3. Okay, we said the MSE was essentially this, right? MSE is this, right? If m equal to n plus 1, show that the mean square error is 0 for some choice of weights. Okay, and what is the geometrical interpretation of this scenario? Okay, I actually touched upon this point earlier when we were looking at m versus n, but I just thought I would put this here for you. If any of you wanted to take a crack at, a sort of a formal proof, and the geometrical interpretation also we talked about a little bit, but it is good to sort of take your own time and understand the geometrical interpretation of this scenario, right? So this is a question that I thought I would sort of ask and give you some time to think over or sort of formally prove. Question number 4, again something that we touched upon. This was a very important identity, remember, in our process for finding the closed form solution. And if you sort of wanted to spend a few minutes expanding this thing out, taking the derivative, taking the gradient, reorganizing the terms, and showing that it's actually A plus A transpose W, you're welcome to do that. Like I said, the proof of this is, I'm going to give a link to it, but it doesn't hurt to sort of challenge yourself with trying to come up with this proof. No new concepts here, like I said. Okay. Question 5. The gradient vector comprises elements that indicate the rate of change of function along each direction computed at a point. We know this, right? But how do we know that the gradient vector is in fact the direction of maximum change of the function at the given point, right? I mean, it is one thing to sort of create a gradient vector. It's one thing to sort of create a gradient vector, which looks like this: delta f over delta x, delta f, delta y, and so on, and put this into a nice vector, right? And you say you sort of compute it at a point x0, y0. But how do you know that this actually represents the direction of maximum change, right? So maximum increase and the negative direction is the maximum decrease. How do you know that it is the direction of maximum change of the function, right? Give it some thought, but that is essentially what this question is, and that is the question that I have for you. Tell me why the gradient actually is the direction of maximum change. Focus on the word maximum. That's what question is about. Okay. Question 6. In gradient descent, why do you move by a fixed multiple of the gradient, right? So with a fixed learning rate, rather than using a variable learning rate and moving by a fixed distance, right? So nobody said that. I mean, why couldn't you just have a scheme where alpha actually changed from iteration to iteration depending upon the magnitude of your gradient vector? So moving by a fixed distance or changing the x and y values by a fixed amount in every iteration rather than having a fixed learning rate. Okay. Why is this? Why is moving by a fixed multiple of the gradient generally better than by moving by a fixed distance? That's question number 6. Again, something for you to think about, something that I used to think about. Question number 7, a little bit tricky, but let me explain this question. I think understanding this question may take a little bit of time. So suppose your training points, okay, m greater than n plus 1 lie exactly in a hyperplane, right, line in 2D. In this case, your y and y hat are both equal and equal to x, w, right? And right here you can, in 3 steps solve this to get the value of W equal to this, which was essentially the equation that you got in the closed form equation, right? Now clearly this is a special case. This is a special case. Why was our general solution for optimal W found earlier exactly identical to the solution for this special case? Okay. Now, like I said, understand the question. The converse is obvious. This is a special case of that general result that we got, right? And therefore the special case is going to be equal to the general case is going to reduce to this for the special case. But why is the general case exactly identical to the special case? For example, why couldn't there be some term over here, which was a function of the error, or the distances of these points from the hyperplane, which goes to 0 if the points are on the hyperplane? I mean, this would have been possible, right? So what I am saying is, why is the equation for the special case exactly identical to the equation for the general case? How come there is, I mean, that is what I would have anticipated, that perhaps there is some term which is a function of the distances of these points from the ideal hyperplane, and because these points were in the hyperplane, that was 0, and therefore it reduced to this. I mean, I could have lived with that. That's my question. Why are the two exactly identical? Try to sort of think about this. Okay, those are my questions. We will need to have another lecture on linear regression. There will be a linear regression part 2, and over there we will cover some of the assumptions, the metrics, etc., the usual stuff that you need to concern yourself with if whenever you study a optimization technique, etc., right? So that's what we are going to do next, but here is where we stop for today. Thank you.